Next, we're going to introduce the logical axioms of Boolean logic. But before we go through each of these axioms individually, let's connect this to the construction of our logical system. So recall when I introduced mathematical logic on the first day of class, I compared it to the frame problem within artificial intelligence. And recall the frame problem, the main goal of that problem was to determine the common sense assumptions that needed to be programmed into the robot in order for it to be able to move blocks from one place to the other. And recall that this was very similar to mathematical logic. So essentially, the logical axioms serve as the common sense assumptions of our logical system. So all of these statements we're going to take to be true statements. So they're the assumptions we make that we take to be true, and then we're going to use them to develop the mathematical truths within our logical system, just like in the frame problem of artificial intelligence, the common sense assumptions were used to help to program the robot to complete the job of moving one block from one place to the other, or stacking blocks on top of one another. Okay, so you will see that each of these axioms is a tautology. So if you go through and check using truth tables or truth table shortcuts, you will discover that each of these are tautologies. But more than that, what we want to look at is actually believing each of these as common sense truths. Okay, so the first statement, or the first two statements, are properties of equivalence. And essentially, what we believe about equivalence is that it doesn't matter in whichever order you establish equivalence, that establishing equivalence of the first two statements being equivalent to the third is the same as establishing that the first statement is equivalent to the equivalence of the second two. So all of these three statements being equivalent together is the same. At the same time, we believe that equivalence is symmetric. That means that it doesn't matter in which order we place two equivalent objects, that doesn't affect their equivalence. So, right, saying that A is equivalent to B is the same as saying that B is equivalent to A. We also have some semantic intuition about top and bottom, because we have established, based on the semantics that we went through in the last section, that top is always true and bottom is always false. So here, essentially what we're establishing is that bottom being equivalent to bottom is true, right? So this statement is true and this statement is true. This introduction of negation is essentially telling us what negation is. So this is going through basically the truth values of the Boolean function for negation, right? So if A is equivalent to bottom, for example, then this means that if this equivalence is true, that means that A and bottom have the same value, which will be false. And if A is false, then A is equivalent to bottom is true. But A being false means that negation of A is true. And so the truth value on either side of this equivalence will be the same. Similarly, if A were true, then this equivalence would be false because they don't have the same truth value. But A being true means that this is false, and so the two truth values on either side are equivalent. We also come to properties of OR. So again, similar to those of equivalence, we know that to take OR of three variables, it doesn't matter whether we group the first two together or the second two together. They turn out to have the same truth value. Similarly, it doesn't matter in which order we take A or B, they're going to have the same truth value nonetheless. If we have A or A, then for sure we have A, and so that's just what that statement is saying. In order to establish the distributivity of OR over equivalence, it works just as you think it would work, where A or B equivalent to C is the same as A or B equivalent to A or C. And you can check that this is a tautology. Finally, this last property of OR tells us essentially that either we have A or we have not A. And so that's a tautology as well. The golden rule tells us that A and B is equivalent to A or B if and only if A and B are equivalent, right? This is going to have the same truth values as this, only if A and B are equivalent, so have the same truth value. And finally, properties of implication tell us that A equivalent to B is equivalent to A or B equivalent to B. And you can work out the truth values of these statements to identify that this is also a tautology. So these are all of our logical axioms in Boolean logic, and they establish the mathematical truths we take for granted, and then we will use these statements to develop other mathematical truths, and we'll see how to do that in the next couple of videos. Okay, so to make this a little bit formal, we're going to use the Greek letter lambda to denote the set of all logical axioms. So recall that these Greek letters are used to represent sets of well-formed formulae. So our sets of well-formed formulae that are all logical axioms, we're going to reserve lambda to represent that collection of well-formed formulae. So recall that the logical axioms are in fact all stated in terms of schema. So remember the last video I mentioned that we were going to be using schema to help us to generalize all of these mathematical truths. So both the axioms and our theorems are going to be stated as schema because what we're really concerned with, particularly in Boolean or propositional logic, is the syntax. So simply the role that the connectives play amongst any well-formed formula. So instead of listing out infinitely many different possible well-formed formula, we want to represent these well-formed formula with variables and identify just how the syntax works on those. And so notice that in this case, lambda, the collection of all logical axioms, is infinite because within any of these string variables, we can put any one of infinitely many different well-formed formula, and we have established with the connectives and the syntax that these are all mathematical truths that we're going to take for granted. So when we mean lambda, we mean taking the well-formed formula represented by the schema. Finally, recall that in section 1.3, when we're trying to develop our intuition, we introduced something called a tautological implication and used the Greek letter gamma to represent the assumptions or hypotheses that implied the tautological implication. And recall that we defined the conclusion of any tautological implication to be a relative truth or a relative theorem relative to the set of assumptions or hypotheses that we had within gamma. So these assumptions are going to be called our non-logical axioms or our special axioms. So if they are true, then we establish the relative truth of the conclusions of these statements. And so we're going to also learn how to construct relative truths as well as absolute truths. Okay, and we'll see later on within chapter 3 that the formalization that we're developing here within our logic is going to be consistent with the semantics, so the tautological implications and the tautologies that we developed in the last section. Finally, notice that gamma is not a fixed set. Unlike lambda, which stands for all of the axioms on the previous slide, gamma is going to change dependent on the statement that we're talking about. Okay, so this is truly a variable and a placeholder for any possible assumptions or special axioms we have in any particular case. Whereas lambda is fixed. It is an infinite set of well-formed formula of the form of the logical axioms that we had on the previous slide. And also note that all of these axioms are listed on our Moodle site, and you'll also be given these axioms for the midterm and the final exam. So these are our mathematical truths, so this is something that you will be given and will be able to use to develop other mathematical truths, to prove theorems or theorem calculations. Okay, so in the next section, we'll further develop our logical system and then finally define what a theorem calculation is.